Hey, and it's working. Great. Got it. So for those of you who are joining us, either on Zoom webinar or via YouTube live stream, we'll get started in about a minute, right at 5 o'clock. Okay, we just hit 5 o'clock, so let's get started. Hi, everyone. Welcome. Thanks for attending the next Flagstaff Festival of Science after-school talk program. My name is Greg. I work with the board of directors of the festival. Joining me tonight are Kathy Ferretta and Virginia Wadahamaji with the festival board of directors, and also Ken Herkenhoff, who's here to talk to us about the history and the latest updates from the Mars rovers mission. We love to remind you all that the Flagstaff Festival of Science is the longest continuously running, entirely free science festival in the world. We're now in our 32nd year, and your participation and your support are vital to our shared success. We couldn't do this without you all and without the support of our generous sponsors and donors. So thanks to everyone for supporting us. So some of you are logged into the Zoom webinar to watch this, and some of you may be watching this via live stream on YouTube. And of course, this will also be recorded and posted to our Flagstaff Festival of Science YouTube page. At the end of the presentation, after the end of all of our events, we would love for you all to fill out a survey and give us your feedback. Let us know how we're doing and let us know how we can improve events for next year. I will put a link to both the survey and to our YouTube channel in the chat window for those of you, so you can see that. So let's get started. Tonight we have Ken Herkenhoff, Dr. Ken Herkenhoff with us. He is a senior research scientist at the USGS Astrogeology Science Center here in Flagstaff, and really a world-renowned expert in planetary science especially when it comes to Mars. Ken's been interested in astrophotography since he was a kid, and he is quite happy to have been able to make a career out of one of his childhood interests, which is amazing. For more than 30 years and still going strong, Ken has been collecting, analyzing, and interpreting pictures of Mars from orbit and from rovers on Mars' surface. In fact, he specializes in the design and calibration of and operation of cameras on Mars spacecraft and robotic rovers. Ken has also been a regular presenter for the Flagstaff Festival of Science After School Talks program, and we welcome him back this year to tell us more. So thank you again for being here, Ken, and I'll take it away.
Well, thanks, Greg. Yeah, I appreciate the kind introduction. Yeah, so let's get into yet another brief history of the Mars rovers. There's a lot to cover. It gets longer every year, which is great. This title slide shows the three types of rovers that have been operated on Mars. All of them were designed and built at the Jet Propulsion Laboratory in Pasadena. 2 rovers are still working on Mars out of the 5 that have flown there. You see there's a couple engineers here for scale. Perseverance, I hope you can see my cursor, is similar in design to the Curiosity rover here on the left with a new payload, and I'll get back to that later. Anyway, I'm very lucky to have been heavily involved in all 5 of these missions, and I thank everyone for your support. So for those of you who are not familiar with Mars, Here are some simple facts. The diameter of Mars is just a little over half that of Earth's. And it so happens that a Mars day is just about 40 minutes longer than an Earth day. And I'm gonna be calling a Mars day a sol in this presentation. But the mass and gravity of Mars is much less than on Earth, only about a third, 38%. So if you weighed 100 pounds on Earth, you'd weigh only 38 pounds on Mars. Its atmosphere is much thinner than Earth's, mostly carbon dioxide, and only 1% the pressure at sea level on Earth. But because Mars does not have oceans, the land area on Mars is actually greater than the land area of Earth. So there's a lot of Mars that we still have to explore. So the first Mars rover was launched in 1997. I'm sorry, it was landed in 1997, the 4th of July. And it was part of a technology demonstration mission. The Mars Pathfinder lander was demonstrated the use of airbags to land on Mars. You can see them in the foreground here, and also carried this first rover, Sojourner, which was intended only to last 7 days on Mars. It ended up outlasting the lander, which failed after 83 days. We don't know what caused the failure, but as far as we know, Sojourner was still working after that time. Hopefully it wasn't too lonely. And because of that success, the Mars exploration rovers, Spirit and Opportunity, were proposed by JPL. At first it was just one rover, but after the 1999 Mars Polar Lander and Mars Climate Orbiter failures, NASA asked JPL to send 2 rovers to reduce risk. And you can see it's much larger. It's also solar powered. It also used the same airbag landing system as Mars Pathfinder. And it was designed to last 90 sols on Mars. And the expectation was that dust would eventually cover the solar panels and kill the power, and that would limit the mission. And its primary goal was to look for evidence of past water on Mars. You can see up at the top here, there's a PanCam mass assembly. There are 4 cameras up there, plus a periscope to feed a spectrometer down inside the body. There are also 4 more instruments on the end of this instrument deployment device, or ARM, including the microscopic imager, which I'm going to focus on today because that was led by the USGS here in Flagstaff. It's only a 1 megapixel camera, which these days seems really small, but at the time for a flight mission, it was state of the art. It's a fixed focus camera, so it has a 31 micron per pixel image scale and a limited depth of field. And so it had to use the arm to move toward and away from targets to get them in good focus. And the MI provided the highest resolution images of Mars until 2008, when the Phoenix mission landed. Okay, so the MER rovers, Mars Exploration Rovers, were sent to opposite sides of the planet. You can see Meridiani here in the center and Gusev here over on the right. This is a color-coded topographic map of Mars, excluding the polar regions, showing low areas in blue and higher areas in red and white. So part of the reason that the MER rovers were sent to opposite sides of the planet were to be so that we could share facilities at JPL in Pasadena to operate both rovers at the same time. So here's Spirit's landing site in Gusev crater, again color-coded topography. Blue is low, red is high. You can see down here at the bottom what looks like a stream flowing into the crater and a relatively flat floor on the crater. Because of these features, we expected that there was a lake in this crater sometime in the past, and that we would find lake bed sediments on the floor of the crater. Unfortunately, when we got there, we discovered that the crater floor had been covered by lava. So if there were any lake beds, they were buried by lava. So we drove from the landing site at upper left here toward Bonneville crater, hoping that it may have punched through the lava into the lake beds. No luck there. So we literally headed for the hills, the Columbia Hills, which were named after the space shuttle astronauts that had perished in that disaster earlier that year, or actually the previous year. And were able to drive up and over these hills, Husband Hill, named after the commander, the last commander of Columbia, Rick Husband, and down the other side toward a feature called Home Plate. This took years, and the rover survived the Martian winters by tilting the solar arrays toward the sun. And we were lucky that winds cleaned the dust off periodically so that we could continue the mission much more than the 90 days it was intended to last. We tried driving toward the lower right here when Spirit's right front wheel drive motor failed on Sol 787, and then spent most of the mission at Home Plate, which was a pretty interesting geologic feature. And then you'd think losing a wheel would be a serious problem. And of course, it's not a good thing, but the rovers, all these rovers are designed to drive backwards as well as forward. So we ended up dragging that right front wheel behind us by driving backwards all the time. And luckily that exposed some very interesting soils that we probably wouldn't have found otherwise. So a classic case of making lemonade out of lemons. And this example here shows some very bright soils that are almost pure silica. And on Earth, silica deposits like this are commonly deposited in hot springs, which is obviously a habitable environment. So this is good evidence that at least this place on Mars was habitable in the distant past. We also found carbonate rock on the south flank of Husband Hill, which was likely also formed in water. So these were the key scientific discoveries of the Spirit rover mission. Here's a microscopic image or panorama of Spirit's underbelly taken when it got stuck in some deep sand. Unfortunately, another wheel failed, one of the drive motors failed, and so it was ended up being impossible to get out of this sand trap. But these images were used to try to figure out ways to try and get out and in planning those extrication efforts. But ultimately, we were not able to tilt the solar panels toward the sun as we had done in previous Mars winters. And so Spirit eventually didn't have enough power to operate anymore. And last we heard from it was in 2010, after 6 years on Mars, much better than the 90 days originally planned. Opportunity had much better luck from the beginning. It was sent to the hematite-rich Meridiani Plains, very flat and safe for landing, and hematite was expected to be formed in liquid water. And here's an image taken from the Mars orbiter camera after landing, showing the first bounce mark from the effects of the rocket firing as it touched down on the surface and then rolled along into this little crater called Eagle, in what the PI Steve Squires called an interplanetary hole-in-one. Here's a picture taken much later in 2017 by the Mars Reconnaissance Orbiter high-rise camera, showing the airbags and lander still sitting there in the Eagle crater long after Opportunity had left. The crater's about 22 meters across. So in that crater, we almost immediately found small spherules that were dubbed blueberries in the sulfate-rich rocks around the crater rim. And many of these are double or even triple berries. And these observations are all consistent with them being, and other rover observations, consistent with the interpretation of these spherules as hematite-cemented concretions, which were formed in place by underground precipitation in relatively acidic water, not as neutral in pH as ocean water, for example. Obviously, I'm leaving out a lot here, but we went from Eagle to Endurance Crater down to Victoria Crater. At that time, Mars Reconnaissance Orbiter had gotten into orbit and started returning data that indicated that there were, clay minerals in the rim of this crater down here. Clay minerals are interesting because they are formed in neutral water and probably record a more Earth-like, a more clement environment than what we had been finding evidence for elsewhere on the sulfate-rich plains here. So it took us years to get there, 3 years after leaving Victoria Crater. We got to the rim in August of 2011, and here's what it looked like. This is enhanced color. The sky is actually reddish, not blue like this. But here are the older rocks with the clay minerals detected from orbit on the skyline, and lower parts of the rim are buried by these sulfur-rich sediments that we had been exploring previously. And sure enough, when we got to the rim, we found evidence for less acidic water chemistry. This is a vein of gypsum, very common mineral on Earth that is precipitated from low temperature water and again, much less acidic fluids. It's a hydrated calcium sulfate. So this was evidence that at least this place on Mars, again, was much more habitable in the past. So again, leaving out a lot, we traversed along the rim toward the south, toward a feature that was detected from orbit. This is a high-rise image taken from orbit of this valley called Perseverance Valley, and it looked like it might have been eroded by flowing water. And so that's why we went down there. And it turns out that when we examined it in more detail, flowing water was not the only realistic hypothesis for the formation of this feature. In fact, perhaps a more reasonable one is that it was just caused by faulting offset along faults and then wind erosion. But unfortunately, as we were examining Perseverance Valley, we ran into a global dust storm that I'll get back to in a second. But before that happened on Sol 5000 in 2018, we used the MI for the first time to take a selfie. Again, it's completely out of focus, but still you get a pretty good view of what the rover looked like on Mars. And now here's sort of a simulation of what the sun would have looked like during this 2018 dust storm that killed the rover. On the left, it's pretty bright in a normal opacity 1 situation. Opacity is a measure of how much dust there is in the atmosphere. And you can see it increasing here till it gets to the point where it just blots out the sun entirely. And in fact, on Sol 5111, the data received indicated the opacity was over 10. So basically plunging the rover into darkness, which caused a low power fault. The Opportunity rover couldn't get enough power from sunlight. And so the last communication we got was on Sol 5111, and the mission was declared complete in February 2019. Again, not too bad. Almost 15 years for a mission that was designed to last only 90 sols. Okay, so on to the Curiosity rover. This is much larger, too heavy for the airbag landing system. So MSL, Mars Science Laboratory, landed on Mars using retro rockets and guided entry for the first time. It's nuclear powered. There's a nuclear power pack on the back here, and it landed successfully in August 2012. It's now in its 3rd extended mission. So the primary goal of this mission, MSL, was to determine whether Mars was ever habitable. So it's looking at the biological potential in the rocks, the geology and geochemistry, the role of water, obviously, and it's also measuring surface radiation, which is useful for planning future human missions to Mars. The payload for Curiosity is highly international. You can see at the top here, the ChemCam, the laser-induced breakdown spectrometer, was partly built by US, partly by France. The weather station, REMS, was provided by Spain. The neutron spectrometer, which can detect subsurface hydrogen, was provided by Russia. SAM, the sample analysis at Mars, was also part French, part US. And then there's a bunch of cameras, a drill, and alpha particle X-ray spectrometer that was provided by Canada. All the international contributions didn't cost NASA anything. So Gale Crater was selected as the landing site for the Curiosity mission because it has a lot of features of interest. First of all, there's a huge 5-kilometer high stack of layered rock in the middle of the crater that's been partly eroded away to expose various types of minerals along its flank, clays, sulfates, and these changes in mineralogy probably record changes in the global climate of Mars, similar to how the rocks in the Grand Canyon record changes in the environment in northern Arizona over the millennia. So we couldn't land right on these interesting clays and sulfates because the slopes were too steep. So this ellipse shows where the rover was targeted nearby to these, and then the plan was to drive up the hill from there. Also, it turned out there was a nice alluvial fan and some layered hard rock in that ellipse of interest. So that all those reasons are why we decided to go to Gale Crater. Curiosity used the sky crane maneuver for the first time, partly because these rockets were expected to disturb the surface, throw rocks around, and in fact they did, even with the rover drop down below it. And I'll show some more pictures of that later. But that obviously was successful. Here's the landing site as seen from orbit, again from the high-rise camera on the Mars Reconnaissance Orbiter. Here's the landing site, and you can see the darker patches where the rocket plumes blew away a lot of the brighter dust. And then I hope you can see the rover tracks going along here, all the way over to where Curiosity was when this image was taken. On the shores of Yellowknife Bay, not really a bay, but it was a target of interest because from orbit, we saw this bedded fractured unit and had some mineralogical information from orbit that indicated this might be a good place to explore. It was less than a mile from the landing, so not too far out of the way. And it turned out that was a good decision to go that way because we discovered mudstones from an ancient lake bed in Yellowknife Bay, evidence for water that was safe for life, less acidic. All the chemicals needed for life were found. And importantly, organic, that is carbon-bearing chemicals were detected. And here's Mount Sharp in the background, that big pile of sediments that was the ultimate goal of the mission. So we checked off a lot of the mission success criteria at this location. Then as we proceeded toward Mount Sharp, as you probably heard, we discovered a lot of holes in the wheels. The rocks were sharper, more angular than expected, but by changing the way that we drive the rover and taking more precautions, we've reduced this wheel wear to the point that it's not expected to limit the life of the mission. We've already gone over 25 kilometers, and the wheels are still working just fine. Testing at JPL and that Mars yard that I showed on the first slide showed that these wheels can be much more damaged than this and still provide the traction necessary to drive on Mars. So as we progressed toward the mountain, we discovered many tilted layers and flat layers as well that we've interpreted as lake bed deposits here where they're flat, and delta deposits where they're inclined. And this diagram at the lower right shows what we've learned from deltas and river deposits on Earth. Rivers, when they flow into open water, produce a delta, and as the sediments fall down the slope into the bottom of the lake, they form these inclined beds that like the ones we see on Mars. Then out farther in the middle of the lake deposits are much finer grained, muddier, and flat lying like we're seeing here at the lower left. As Ryan showed, we explored active sand dune. Orbital image showed that these dunes are migrating, every year essentially. So they're currently active. So we got in there, scuffed with the wheel to get some information on the interior of the dune. And as Ryan said, these small ripples are common on Earth, but the intermediate sized bed forms that we're seeing here are unique to Mars. Okay, we've drilled a lot of holes in Mars. The drilling is necessary to feed material into the laboratory instruments Sam and Kim in on the interior of the rover to learn more about their mineralogy, chemistry, and other properties. This shows a sampling of some of the earliest drill holes. In the sort of the middle of the mission, we had a problem with the drill, but that was solved, and we've since been able to drill again, and now have drilled 33 holes in total. Clays and organics were found only a couple of inches below the surface. This was a major finding of the mission because we didn't know how deep the radiation damage on Mars that's expected on Mars would extend and eliminate or break down organic material. The solar ultraviolet radiation and cosmic rays are constantly bombarding the surface of Mars because its atmosphere is not as thick as Earth's. But this is good news that only a couple inches below the surface, organic material is preserved. So this increases our chances of being able to detect life or evidence of life if it's there. This is a few days old, so the rover has actually gone a little bit farther than shown here. But here at the top is the landing site. We went over to Yellowknife Bay and then had to go around these dunes because they're not easily traversable, and have been climbing up the side of Mount Sharp or Aeolus Mons ever since then. We are seeing transitions in the types of rocks as we drive up here, from clay to sulfates. And so we're learning a lot about the evolution of Mars's climate, and plan to continue driving up in the near future. So yeah, stay tuned for more on that. But now let me move on to Perseverance, the latest rover. Again, very similar design. Almost exactly the same design as the MSL Curiosity rover, but different payload. It's also got more robust wheels, so we haven't seen any damage. Instead of just a drill on the end of the arm here, it's got a coring bit so that cores can be acquired and cached on the rover, and eventually hopefully return to Earth. And I'll get back to that, but that's a major goal of this mission, is to begin progress towards sample return. It was successfully launched last year on July 30th. Normally, the science team meets to have discuss plans for the mission in Florida, but we couldn't do that this year due to COVID, but it was still obviously very exciting to see a successful launch online. Again, the payload is very international. This time we've got a ground penetrating radar system that's provided, called RIMFAX, provided by the Norwegians. There's an experiment to produce oxygen from Martian CO2. That's all of these have been run successfully now. SuperCam is a better version of the ChemCam laser microimager that now is jointly provided by Spain, France, and the U.S. Again, the weather station was provided by Spain, and we've got a bunch of cameras, 23 cameras total on the vehicle. The helicopter is not shown here. It was carried below the belly here, and I'll get back to more details on the Ingenuity helicopter shortly. But again, the primary goals are to determine whether life ever existed on Mars, and to select and cache rock and soil samples for potential return to Earth. So here's a diagram, a simplified diagram of the very complex sampling and caching subsystem on Perseverance. As I said, there's a coring drill on the turret that can then put cores into this bit carousel. They can be then manipulated by the sample handling arm, stored in one of 43 tubes. We have potential to gather up to 42 samples. There's a sealing station. designing, testing, and verifying that this was all going to work was a huge effort at JPL. But it's been tested out and so far is working extremely well. Here's a picture at the lower right of give you a feeling for how big these cores are. This is one of the sample tubes. You can see the dimensions here, about 5 centimeters long. The core sample is about 5 centimeters long, a centimeter in diameter, and about 15 grams each. Hopefully, and I'll come back to this, these tubes will be placed in a rocket for launch off of Mars into orbit and eventually be returned to Earth. And an international return mission is currently being studied. But first, let me show you how the landing worked. The Jezero crater landing site was selected because there's the remnants of a delta here in this side of the crater. Here's the crater rim. And you can see a stream valley flowing into the crater and then forming this delta. Apparently the crater was filled to the brim at one time because out of the field of view of this image, there's an outlet channel eroded into the far rim. So we expect to find a lot of fine-grained sediments that could potentially preserve signatures of life on the floor of this delta and maybe in the delta sediments as well. This is a good place to go on Mars because on Earth, deltas are just teeming with life. So that's why this site was selected. One of the new aspects of the landing system for Mars 2020 Perseverance is what's called terrain relative navigation, or TRL. The way it works is that the rover takes pictures looking down at the surface during descent, compares them to an orbital map that it has on board, stored on board in the computer of the rover, and uses it to decide if it needs to divert if necessary. And as I'll show shortly, it worked perfectly and landing was successful. But a key part of this is the map that the rover uses to compare what it's seeing on descent to figure out where it is. And the USGS team in astrogeology created the most precisely aligned image mosaics of Mars ever to support this landing. So the high resolution mosaic shown here, you can't see the full resolution, you could really zoom into this, was used to map hazards at the landing site. And then a lower resolution of this mosaic, along with a hazard map, was stored on board the Perseverance rover. And the computer, as I said, used it to steer away from hazards during landing. So next I'm going to show a video that combines the activities in the mission support area at JPL with images that were taken from the rover as was landing. In fact, it looks like this was all happening in real time, but because Mars is so far away from the Earth, there's a delay of several minutes. So by the time these images were, or by the time the radio signals were sent from the vehicle back to Earth, they had already happened several minutes ago, and you can't just joystick the lander. So basically, these engineers are just watching what's happening and hoping all goes well. So I'll start the video.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance has now slowed to subsonic speeds, and the heat shield has been separated.
That's Mars in the background.
This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
OVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
Here comes Sky Crane.
Sky crane maneuver has started.
That's looking
about
up
20 meters off the surface.
and looking down at the left.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
Woohoo! All right, I still love seeing that. Yeah, so obviously everything worked extremely well. And here's a picture taken again from high rise in orbit of the damage we did to the landing site. So here's Perseverance, the heat shield impacted over here on the right. Descent stage, you saw it flying away in that video at the upper left. It flew safely away from the rover and crashed over here. And here's the parachute and back shell. So here's some close-up views of these from high rise again. You can see a bunch of blue colored debris here from the crash side of the descent stage. As expected, it had done its job and just crashed safely far away from the rover, which is shown here. Again, plumes from the descent engines blew away some of the material on either side of the rover. We probably won't visit these features. It's probably a little too dangerous and out of the way, but we'll see. So as I mentioned, the Ingenuity helicopter was mounted on the belly of the rover underneath. It was covered by a shroud initially, which in this view has been deployed. It was dropped onto the surface and then the rover drove away from it. Here's a couple of legs of the helicopter which were deployed, and then the helicopter was dropped on the ground. And then here's a selfie taken by the Watson camera on the end of the arm of both the helicopter and the rover after the helicopter had been dropped off, and then the rover drove away from it so that it's free to go. It has its own telecommunications hardware. It's got a little solar panel so that it can recharge every day. And then the first flight included this aerial color photo, first aerial color photo of Mars from a helicopter. Here's down at the bottom, the shadow of the helicopter, and you can probably see some of the tracks from the rover in the background here. The technology the Ingenuity helicopter is a technology demonstration, as the Sojourner rover was on Mars Pathfinder, and so far it's gone extremely well. Here's another video that I would like to show you. I'm going to get to the good part here. here comes the helicopter in from the right. For this test, it flew like 100 meters laterally and landed in a new location. Before it landed, it was flying along at about 5-meter elevation. You'll see it go up to 10-meter elevation here as part of this test, and then it'll go back down and land on the surface. More similar tests have been done, and they all went so well that the helicopter is now being used to scout ahead of the rover, so it can fly to places where the rover hasn't been yet, take pictures from a good height, and send them back to the rover, and then eventually back to Earth, so that we can use them to plan future rover traverses. So nobody expected that the helicopter would possibly last this long and be able to provide this kind of support for the mission. So this is just all gravy, and it's been wonderful. The helicopter has now completed 13 flights successfully, and we're still contemplating future flights to continue the mission. Okay. Even more importantly, 2 samples have been successfully acquired from this rock called Rochette. Here's the first hole, and here's the second one. We confirmed that there was a sample in the tubes in both of these cases. We were a little disappointed. The first rock we sampled was so crumbly that the core just fell out of the bit and was not recovered. So we picked a harder rock, and this gave us some good samples. So those have been safely cached on board the rover, and hopefully will be returned to Earth someday. And here's the Notional 3-mission Mars sample return campaign that I mentioned earlier is currently being studied jointly with the European Space Agency and other international partners. So at the far left, we're doing the sample collection right now. That's Mars 2020 Perseverance. The next mission would send a rover and a Mars ascent vehicle to land near wherever we cache the samples, wherever we decide to cache the Perseverance samples. The fetch rover would go out and grab them, put them in the Mars ascent vehicle, which is then launched into orbit around Mars. Then the third mission rendezvous with the sample container and grabs it and then returns it back to Earth. The earliest the samples will be returned is something like 10 years from now. It's probably going to take a little bit longer than that, but still, this is very exciting. The Mars sample return has been the holy grail of Mars exploration for decades, and I'm really looking forward to seeing those samples back on Earth. The major advantage of returning samples to Earth rather than trying to analyze rocks and soils on Mars is that they can be analyzed, once you get them back to Earth, they can be analyzed using the latest state-of-the-art instruments in laboratories around the world, and can be saved for analysis as future better techniques are developed. So we really stand to learn a lot more from these samples than we ever could just by doing experiments on Mars. The Apollo lunar sample return is a good example of that. We've learned a lot about the moon from those return samples. So we're looking forward to that. And so I'm going to leave this up for a few minutes while I take questions. These are some websites and Twitter feeds that can help you get more information on all of these missions. Again, I'm really happy to be involved in these missions and looking forward to the future exploration. So I'll leave it at that and take any questions you might have. Thanks for your attention.
All right, just imagine you hear all the thunderous applause. That was great, Ken, thanks. So those of you who are listening, feel free to start shooting questions in the Q&A box or in the chat. I'll see them if they come in the chat too, but we're trying to use the Q&A box for questions. let's see, we have one coming in. First question, Ken, is would you rather have soil samples rather than rock cores? Sounds like they'll fall out of the sampling tubes like your crumbly rock.
There is, yeah, that the problem with that crumbly rock was that we were expecting it to be a solid sample. There is a plan to and hardware to acquire soil samples, so we can acquire soil, and we probably will. The advantage of returning rock samples is that they have been less weathered, less affected by the environment. They're more pristine, and therefore record better the early history of Mars, which is what we're really after here. So yes, while we will acquire soil samples, and those will be useful as well for understanding those weathering and other processes that have affected the soils, the main goal is to return hard rock core samples.
And I have sort of a follow-up to that. So the first one that you tried, all the rock was just too broken up and it all fell out of the tube, right?
Yeah, that's right.
What does that say about the type of rock? Was it different from the other rock that you sampled?
Yeah, that's a good question. Yeah, obviously it had been more weathered. We abraded it first so that we could look at it, close up and relatively clean surface before acquiring the core, and that went pretty well. So it was kind of unexpected. I think, yeah, it's just what geologists call a very friable rock, so granular and evidently so weathered that it just, yeah, again, just fell apart when we tried to drill into it. But because, yeah, so that it tells you something about how much more that rock had been weathered. Maybe it was weaker and more porous to start with, and then when fluids flowed through it, it got even more broken down. We don't know for sure, but that's a likely scenario.
But the sample tube was sealed and it's going to come back, right?
We don't have to return all the samples, but yes, it was sealed, and there's maybe just a few specks of dirt left inside of it. But it has an atmospheric sample in there, so it's not a complete waste. But that, clearly that's not not going to be one of the top priority samples for return to Earth.
Unless you're an atmospheric scientist.
Well, we can also do just pure atmospheric samples, and we'll probably do that as well.
Great. Okay, here's a couple more questions that are related, so I'll combine them. Is there going to be a future rover mission on Mars in the next few years? And considering how things tend to last much longer than anticipated, how long do you think Ingenuity helicopter will be in use?
Boy, that's a good question. I've given up on predicting how long these rovers and other equipment will last because I keep getting surprised. Obviously very well engineered and well designed. The next mission, hopefully, as I was saying, will be the Fetch rover and Mars Ascent Vehicle mission. So that's being currently studied by the Europeans. The Europeans are intending to provide that Fetch rover with the and give it the capability of gathering the samples. What we're going to do is select a place. Once we've got a bunch of samples, we can then drop them on the ground for later pickup. And so we'll pick a place where after we've got a good set of samples, where we can drop some or all of them onto the surface for this Fetch rover to come pick up. So it has to be capable of grabbing the samples off of the ground and putting them into a container that will then be placed into the Ascent vehicle, the rocket that will launch them into Mars orbit. So that mission has not been approved by either ESA or NASA yet, so there's still ways to go, but hopefully that'll be the next mission in this sequence.
All right, sounds good. there's another similar question about, what's going to happen next, and how long do you think Perseverance will last? Delving more into that, like Perseverance is powered by not solar power. It's powered by how is it powered, and how long will that last? That's the question.
Yeah, no, that's a good question. And we have actually good experience with that from Curiosity. Curiosity and Perseverance both use the same nuclear power pack. It's a thermoelectric, let's see, what's it called? I can't remember the actual name of it. Basically, it's got plutonium oxide, which generates heat that is turned into electricity to charge the batteries, which then run the rover. Curiosity has been there since 2012, still going strong. Last I heard from the project manager, they have some tricks up their sleeves for how to get more activities out of limited power as it decreases. I should have said this plutonium power source slowly decays over time. And so, yeah, unlike the Mars exploration rovers, which were solar powered, we know Curiosity and Perseverance are not going to last forever. So eventually the power will dwindle to the point where we really can't do much anymore. At first, maybe, okay, we can't drive anymore, but we can still use the arm. Okay, and maybe we can use the arm, but we can't use some of the more power hungry instruments to do certain experiments. So that, we'll slowly use capabilities along those lines, but that's still years ahead. So I would predict that Perseverance will probably last another 20 years on Mars, but that may be optimistic. We'll see.
All right. And there's a comment from Alex Swain saying he believes it's called a radioisotope thermoelectric generator.
That's it, RTG.
RTG.
Thank you.
All right, thanks, Alex. Cool. Well, we still have time for more questions if you want to ask them. I have another question about water. What happened to all the water that is liquid water that was once present on Mars's surface?
Yeah, as Ryan said in the previous talk, a lot of it is locked up in water ice, both at the poles, at the surface of the poles, so we can see water ice, particularly at the North Poles, and then there's ground ice at higher latitudes, and maybe even down, toward the equator at greater depths where it's more insulated from sunlight. So part of the water is still on Mars as ice. But based on the results of the MAVEN orbiter, which is still gathering data up there around Mars, most of the water was lost due to escape from space. As I said earlier, Mars only has about the third of Earth's gravity, so it's a lot easier for molecules, gases to escape from the top of the atmosphere. What happens is they get hit by solar UV and cosmic rays and get broken into hydrogen and oxygen atoms. The water gets broken into hydrogen and oxygen atoms, and then the hydrogen, because it's so light, can easily escape. So that's where most of the water went.
All right. There was a second question to another question that somebody asked earlier about how long it'll last. Where will Perseverance be going next? And sort of to follow up on that, when will it reach some outcrops of the delta, which is sort of one of the main geologic targets?
Yeah, the plan, the near-term plan is to acquire some more samples at the floor of the crater. We want to get a variety of samples, obviously. And for those of you who heard Ryan's talk previously, in particular, lava samples are valuable because they can be used to absolutely date the age of those rocks, so we can tell when those lavas flowed on the surface and froze. So we want to do some more of that, and just because of the details of where we landed and the terrain around us, we have to sort of circle back. We've already gone 2.5 kilometers, so over a mile, but then we have to circle back to get toward the base of the delta, which is obviously a high priority goal. And we, even before landing, potential traverse routes were selected using high-rise stereo data, digital elevation models, to determine where it was safe to drive, where the rover could climb. And so we've got a long-term plan for not only examining the base of the delta, but driving up onto it, and eventually up along the stream bed that fed of the bed of the stream that fed that delta. That'll take years, but we intend to gather. The goal is to cache 20 samples by the end of the nominal mission, which is about a year and a half, Earth year and a half. So we're getting there, but yeah, hopefully it'll last much longer than that.
Okay. There's still time. So here's another one about human missions to Mars. What do you think, roughly, about when a human mission to Mars might happen someday?
Yeah, that's a good question. That's been obviously planned for a long time, and it's very expensive. The question in my mind right now is who's going to be first? Elon Musk has been saying that he's planning for SpaceX to land people on Mars in the near future, next few years. I wouldn't expect anybody on Mars until the next decade, the 2030s sometime. But hopefully I'm wrong. I would love to see people walking on Mars in my lifetime. So yeah, hard to say, but hopefully soon.
Yeah. And here's where I wish we had a live studio audience so we could say, who wants to go to Mars? Just one more question from me about the future Fetch rover that's going to pick up the cached samples. I assume it will have navigation cameras on it, but will it also carry other scientific instrumentation, spectrometers, cameras for doing science, or is it just going to collect the samples?
I don't know. That, as I said, that mission is still in the design phase. And I am not very familiar with what the latest is, but my expectation is that it won't have too many more instruments than what are needed to ensure that the samples can be collected and brought back to the lander safely. Maybe we can sneak in some science experiments, but it's already expensive enough that I think there's going to be some resistance to doing that. It just adds mass, power requirements, complexity that would increase risk of to the whole mission. So I don't expect too many science instruments on that next mission.
All right. Well, we're just about out of time, so I want to thank Ken again, and thank you to all of our sponsors. Thanks for tuning in. For those of you who are still on, please check out our survey and let us know how we're doing after every event you attend. There's a link to the survey in the chat. And also, if you want to watch this talk again or any of our other talks, you can go to our YouTube, the Flagstaff Festival of Science YouTube page to see the talks that have been recorded. So thanks a lot for joining us, and we'll see you at the next Flagstaff Festival of Science event. Have a good night, everyone.
All right. Thanks, Greg.